We'll start this video off with a warm-up question. Everyone who watched the last few videos should be able to do these two questions very quickly. Find the derivative with respect to x and the derivative with respect to y. Remember, this dy dx is the same thing as the slope of the curve, and d squared y dx squared is the same thing as the concavity of the curve. So, we start with dy dx. We need that before we can find the second one. So dy dx will take the derivative of y on top, so that's going to be 3t squared minus 3. And the derivative of x on the bottom, that's going to be 2t minus 2. Swell. All right. So we could barrel on through with the second derivative. And as we saw at the end of the last half of this section, the second derivative can get pretty gnarly pretty fast. So if we can find anything that might make our lives a little bit easier, then perhaps we should. There's a hint. Okay, and probably a lot of you guys are noticing that there is something we can do to make this answer a little bit easier, maybe more than a little bit easier, and it's factoring. We can factor out a 3, and then it's a difference of squares, and we get that, which in and of itself is not simpler, but then if we factor out the denominator as well, we'll see, aha, ooh, this is nice, because then we have, instead of a rational expression, we have a simple linear expression. Oh, okay, cool. So there's our first derivative, 3/2 times t plus 1. And that's kind of nice because then when we take our second derivative in green, we don't have to worry about the quotient rule. Good news. Remember, that's going to be the derivative with respect to t of our first derivative divided by dx dt. Now, here's where some people will make a mistake. They'll just say, oh, I'm just going to multiply by 2 because that's the denominator, right? And this is the denominator of the last one. No, 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 no. The denominator over here is not the same as dx dt. We need to go back to the original expression before it was reduced. So be careful with that. But if we take the derivative of the numerator with respect to t, we get the very simple 3/2. Hooray! And then the denominator becomes 2t minus 2. And then we end up with 3 over 4t minus 4. Or you can factor out the 4, whatever floats your boat. But anyway, give it a try without simplifying and see if you can eventually get to the same answer. You're going to have a lot of extra stuff floating around and a lot of reducing to do. So if you're feeling faint at heart, then perhaps you should wait until you've eaten a good breakfast and you're ready for it. But yeah, this should be the easiest way, I think, in this case, to find that second derivative. All right, cool. So that was our warm-up. Now we're going to explore this curve a little bit more. Whoa. And ask the question, what is dy dt, or I'm sorry, dy dx, when t equals 0? Well, we might say, well, that's easy, right? We just found that, right? We know that dy dx is this. It's 3/2 times 1 plus 1. Oh, that's just 3. Fantastic, so easy. Okay, but wait a second, hold on. Is it really? If I take t equals 1 and I actually plug it into the original expression, I'm going to get 3 minus 3 over 2 minus 2. That's going to be 0 over 0, which is indeterminate. Remember that this original fraction is equal to this fraction, provided that t does not equal the thing that was causing problems. Provided that t does not equal 1. So perhaps as the graph gets very, very close to t equals 1, our slope gets very, very close to 3. But what happens at t equals 1? And that's an interesting question that might be a little bit hard to answer unless we pull out the big guns, a graphing calculator. So we all know that Desmos is the best graphing calculator. So we'll go ahead and graph a parametric curve. Yeah, we can graph parametric curves in Desmos. We just plot it like a point, right? So remember, we have an x value and we have a y value. We just have them in terms of t. So what is the x value in terms of t? Well, that was t squared minus 2t minus 2. That was the x value that we were given. The y value was t cubed minus 3t. And that's not a very interesting curve, is it? It's just a little bitty line segment almost. Oh, wait a second, that's because t is only going from 0 to 1. So let's maybe go from negative 10. Oh, there's a little bit more of that graph. Kind of a nice little almost parabola type thing. And then we'll change this to positive 10. What? How strange. It's like this thing comes along and bounces off some invisible force field at the point negative 3 comma negative 2. I wonder what the t value is at that point. Well, here's something nifty we can do. We can copy and paste this, and we can change that t to any other variable. Well, I like to use a. And then we can create a slider. And we can let this slider change values, and we can see the values of t for any point. And we can slide this back and forth and have a good time with it. And we notice, perhaps unsurprisingly, that the t value of 1 is that interesting point that does not seem to have a derivative there, right? It seems like that's the one place where this is not a nice smooth curve. All right, so that's kind of interesting. I wonder what the slope would be if we had differentiability there. Well, I mean, a good guess would be 3, right? At this point, which happens to be negative 3 comma negative 2, we'll maybe pick our tangent line. We'll say negative 2 is the y value, equals negative 2. And then we suspect that the slope might be 3 times, oh, maybe we shouldn't use t, should we? Times x minus negative 3, or plus 3. All right, so let's get rid of the t here and change it to an f. There we go. So now we can see that that purple line sure does seem like it's a local linear approximation, at least on one side of that point. In fact, I can't resist the urge to zoom in on this and see what it looks like. And yeah, I mean, of course, our purple line continues on for x values less than negative 3, but our original curve doesn't seem to go past that negative 3 mark. But yeah, as we zoom in on that point, on the right side of the point, that purple line seems to be a good local linear approximation for both pieces of that red curve. Okay? Because whether we're approaching t from the left or from the right, our limit is still going to equal 3. So here's a nice little way to see what's going on. All right, cool. So what else does it ask us to check out here? It asks us to find, this might not be quite as interesting, I guess, but still something that's likely to be asked. We're going to find all the points of horizontal tangency. Okay, so of course, we can see that it looks like there's one right here, but let's pretend like we don't know that. How do we find that? Well, we say we're interested in when dy dx, which is the slope, is equal to 0. Okay, so the danger here is that we would set the numerator equal to 0 and get t equals 1 and t equals negative 1 as two different values of t that will cause that that slope to equal 0. But remember that this is going to equal 0 only if the numerator equals 0 and the denominator does not equal 0, right? If they both equal 0, then perhaps we have a horizontal tangent line, but as we just discussed, we don't. We have a slope of 3 there. So the moral of the story is don't just set the numerator equal to 0. Make sure you double check and make sure we don't get a 0 in the denominator. So long story short, make sure you're using the simplified version if you want to keep things simple. So 3 halves t plus 1, 3 halves t plus 1 is equal to 0, means that t equals negative 1. Have I answered the question? It says find all points of horizontal tangency. I haven't found the point. I've only found when we're at that point. Now we need to figure out where we are when t equals negative 1. So the x value is going to be negative 1 squared, that's the t squared, minus 2 times negative 1, that's the minus 2t, and then minus 2. That was the original equation that was given. So that's 1 plus 2 minus 2 is 1. And then the y value was t cubed, or negative 1 cubed, minus 3 times negative 1. That's negative 1 plus 3 is positive 2. So the point is 1 comma 2. Let's pull up our graph and double check if the point 1 comma 2, that looks right to me. Sure does seem like a place where the tangent line is horizontal, and it sure looks like it's the only point as well. Now, if we ask about points of vertical tangency, we would say, well, when is dy dx undefined, right? Well, we did find a place where it was undefined. It was undefined at t equals 1, right? Because we got a 0 over 0. But did that mean we got a vertical tangent line? It didn't, right? We had a slope of 3 instead. So actually what we need to say here is not an indeterminate undefined, but a number, a non-zero number divided by 0. So in other words, we're looking for places where dx dt is equal to 0 and dy dt is not equal to 0. And there is only one t value where dx dt is equal to 0, and that's t equals 1. But turns out that is a value that causes dy dt to also equal 0, right? That's that common factor of t minus 1. So if we just look at this simplified version and we say, well, when do we get a number in the numerator and 0 in the denominator? Well, never, right? 0 is never going to be in the denominator of this expression. So the moral of the story really is just use your simplified version, and that will save you some headache down the road. So this never happens. No point of vertical tangency. All right, and again, looking at the graph, of course we don't see all of it, but if we zoom out, we can be kind of convinced that there's never going to be a place where there's going to be a vertical tangent line. You can scroll up and you can see that this kind of keeps on increasing with a positive slope, and you can scroll down here and you can see that this keeps on decreasing with a negative slope, but we never have a vertical tangent line.